Now, let's go ahead and address bond strengths and bond lengths. So these kind of go hand in hand. Let's start with bond enthalpy, just the concept here. Essentially, it's the stability, or the concept is that with bonding, remember that the molecules are held together by these covalent bonds, and pretty much the more stable it is, the more strong its bonds are. The strength of a covalent bond is determined by the amount of energy required to break the bond. So the reason why, and again, any bonds form is because they become more stable with the bond. And so the strength is basically saying how much energy does it take to break apart that bond, just how strong is their connection. So the definition for bond enthalpy is a specific enthalpy change. Remember, enthalpy change is any sort of energy change of breaking a specific bond in a mole, it should say mole, of a gaseous substance. So let's take a look at this. The bond enthalpy of chlorine gas. If you take a look at the arrangement here, chlorine gas on the left is going to be separated into the individual atoms of chlorine, and this does require an input of energy. As a review, the delta H should be a positive sign because it requires the input. Right, your final products here, the two chlorine atoms, is higher in energy than your original Cl2 that was stable because it had formed a bond. Couple of notations you need to know, at least when it comes to this. Essentially, they like to use this anyway, is a couple of terms. I think they like to use the letter D, and then it's going to have the ClCl inside of it. So that the amount of energy it takes to break apart this bond is represented by the D, and then the bond that you're referring to is in parentheses. And that's essentially it. So anytime you see a bond you want to deal with, go ahead and put the letter next to it, or the D in front of it. You don't need to do anything here. There's no way to represent this because it's not a bond, so that doesn't make any sense. And in this case, the bond energy it takes, so the amount of energy it takes to separate the chlorine-chlorine bond ends up being 242 kilojoules per mole. Okay, let's move on. Your average bond enthalpy. So this is a concept that kind of applies more to how they do it. So for example, here you see that we're trying to break apart methane. So one simple bond, where it's a single Cl-Cl bond versus a CH4 where there's several CH bonds. How exactly do you calculate that? Well, it turns out that you can really just use something called atomization, which then you go ahead and take the average. So find the energy required to break it all apart, and then divide it by 4 for the fact that you have 4 4 of those bonds. So that means the bond enthalpy of the CH bond is actually a quarter of the energy it takes to break apart the entire structure into its individual atoms. Here's a list of them. It's in your textbook in chapter, or at least in chapter 8, table 8.4. It's on page 326. And this is essentially the list of bonds. Now notice again, the first chunk is all about the single bonds. The bottom chunk, little section down here, is the multiple bonds that you have to pay attention to. So make sure you're looking out for the correct one when you're doing these calculations. Speaking of calculations, how exactly do we determine enthalpies of reactions? This should be a bit of a review. So you all should remember from the past, how do we determine enthalpies of reactions? Well, one way to do it is with calorimetry. So there's that negative Q is equal to H sort of thing. So solve for the delta H by knowing how many Q per mole, how much Q per mole there was in the energy process. Also using heats of formation, if you remember this, it was a sum of all the products minus the sum of all the reactants by using the heat of formation of those specific products and reactants. So that required you looking in the back of the book. And also Hess's law. So if I was given a series of reactions and I needed to know the reaction of all those, the enthalpy of all those reactions combined, I could calculate it. So what's the new method? We're going to use bond enthalpies. So this is a great way to approximate how much energy it takes to make a reaction go simply by looking at the specific bonds that are going to be broken and formed. Here's a general formula. So delta H of reaction, you should recognize that for that notation here. That reaction again, delta H of reaction again is going to be your enthalpies of the bonds broken minus all the sums of the enthalpies of the bonds formed. So it's very similar to what we saw before. Make sure everything is accounted for and then sum those up and then subtract the two sides. As a schematic representation, it's a little cut off at the bottom there, but as a schematic representation here, you kind of have the original, say, for example, chlorine. We're going to make chlorine react with methane here. And at the very beginning, they have some amount of energy represented by this blue line. When you want to make this reaction happen, well, we're going to just kind of basically put a single chlorine onto this carbon and take this hydrogen and put it onto this chlorine. So let's go ahead and take an amount of energy to break apart each of those. So again, you're going to increase the overall energy because it's required to break bonds. Remember that inputs of energy is always required to break bonds. So that you have a free hydrogen and then a free chlorine as well. Now, when it comes down to it, you also have these single floating things here that will eventually come together. And the forming of a bond is always going to release energy because, of course, it becomes more stable. So that means your energy will drop down here so that when you form both the chlorine and the rest of the carbon molecule, and when you form the hydrogen chlorine bond, that'll release a lot of energy. So we're essentially trying to calculate how much energy changed when you make this reaction occur. Now, how do we make that happen? Our delta H of reaction, we can calculate that again just by looking at bond enthalpies. So here's the rundown. All right, so your example you can look at here as another one is to use your molecule ethane here, which is 2 carbons and 6 hydrogens. And then you have this sort of 7 halves oxygen, trying to keep it simple, with CO and all the 3 OHs. So this, again, is helpful to be able to do it if you know how to draw out Lewis structures. So identifying Lewis structures is vital here. Also, you should know that O2, even though I don't show it here, if you drew it out, would be a O, double bond O, and then you can calculate or look for the correct amount of energy for that bond enthalpy. Now, I'm not going to sit here and do the entire problem out for you, but if you kind of do it, you kind of going to have to look at the bonds formed and bonds broken. So if you look at this, you kind of take a see what happens here. Well, I have a carbon, again, that's now bonded to 2 oxygens, doubly bonded to 2 oxygens, whereas before it didn't have that at all. So we know that these bonds all broke apart. So you have a single CH bond, but 6 times. So CH bond, CH bond, CH, 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 all those are broken. So you have 6 times a single CH bond of what's broken. So you want to do 6 times, and looking at the data that you're given, it'd be 413. And then you also have to add the bond here that's being broken as well, which is the carbon-carbon bond. And looking at the chart, that's going to be 348 kilojoules per mole. Also, all of these oxygen-oxygen bonds are completely broken, so we have to account for that as well. And since we have 7 halves of those, we do 7 halves times those oxygen values, which again in the book you'll find that it is 495. By the way, they kind of left it off in the book. They don't really represent it as OO like this because really there's a lot more chemistry involved here than making it a single double bond, an actual double bond. So they kind of want to leave that ambiguity out and leave it there. Right, so this is again the sum of all the bonds that are broken, and then we can come over here and look at all the bonds that are formed and add those up. So again, I'll let you take care of the rest of this. So you'll see that if you add up all the chlorines and all the carbons and oxygens, and then go through and add up all the hydrogens and oxygens, make sure you count for the coefficients there in the front. You'll find that the final answer is going to end up being negative 1416 kilojoules of energy as your delta H of reaction. Right, so without even having to perform the reaction, I can approximate the actual reaction enthalpy change just by looking at the bond enthalpies. Pretty powerful stuff. And again, you can run through this example. So if you're going to look through the book and go ahead and look up the values, you can calculate that. I'll pause for just a moment so you can do so. And the value is, for the delta H of reaction, your delta H of reaction here should be negative 86 kilojoules. All right, so you'll see another exothermic reaction that releases energy in this process. Finally, let's go and wrap this up by talking about bond lengths. This is nothing particularly confusing or difficult to understand. All you have to recognize is that pretty much when you have more bonds between 2 atoms, you end up getting a shorter bond. So if you have increasing of bond character, so a single bond up to a double bond up to a triple bond, you end up kind of not only strengthening the bond, so you can see 348, 614, 839, but you also shorten it because, again, the attractions just become that much greater, bringing them closer together.